With regard to cache design, we'd like to answer questions like which protocol is best, which cache line size gives the best performance, what kind of misses are there in certain benchmarks. Questions like these are best answered by simulation. Getting the answer right is part art and part science. You don't really know what kind of workload to use and what level of detail to use in the simulation. If you use too little detail in the simulation, then the results won't be realistic. If you use too much detail, it will take you so long to simulate that you can't cover a realistic range of parameters. And choosing parameters for the simulator, of course, is an art. The examples that we're going to go through first are from the Color and Sing textbook that we used to use for this course. It was 22 years ago in 1998 that they selected a single four-way set associate of 1 megabyte cache to simulate. Their cache had 64-byte lines. The simulation assumes an idealized memory model, which assumes that memory references take constant time. Of course, that's not realistic due to the effect of contention. The simulated workload consists of several programs from the Splash 2 suite: Barnes, LU, Ocean, Radix, Radiosity, and Raytrace, and one multi-programmed workload consisting of mainly serial programs. The first comparison was invalidate versus update protocols. With regard to miss rate, which protocol performs better, update or invalidate? Looking at real programs, we find that all of the benchmarks shown here have quite a lot of coherence misses. You can see true sharing and false sharing in Ocean, and you can see an even greater amount of true sharing and false sharing relative to the number of misses in Radix. So there are a lot of coherence misses, and you can see here that update performs better, in other words, a lower miss rate, than invalidate or a mixed protocol where we sometimes use update and sometimes invalidate. And the same is true for Raytrace and also for Radix. Over here you can see that the update protocol has fewer misses. But that's because there are a lot of coherence misses in these applications. If instead we had a lot of capacity misses, then update wouldn't be favorable because it would keep sending all of the updates to all of the processors, and that would have the effect of keeping blocks in the cache that would occupy lines that were needed for more data to be brought in. So we'd have even more capacity misses if we kept that data in the cache. But miss rate is not the only story. With respect to bus traffic, well, it really matters which protocol gives less bus traffic, because that has a great effect upon bus contention and the speed with which a program executes. So we'd like to compare bus upgrades in the invalidation protocol when you have a block in read-only mode and then you want to move it to read-write mode. We want to compare those with the number of updates that occur in an update protocol. See, the reason we compare these two is they produce bus traffic. So which of them are going to be more frequent? Well, we find that updates in an update protocol, as you can see here, are much more frequent than upgrades in an invalidation protocol. So which protocol causes more bus traffic? Well, that's the update protocol. You can see I don't know if we can see that directly from this graph, but it is certainly true that when there are a lot more update transactions, then there's going to be more bus traffic than in an invalidate protocol. So the situation with regard to invalidate versus update is that update does give you a better miss rate, but it also increases bus traffic to the point that it's usually not the best protocol to use. Now we want to look at the effect of cache line size on miss rate and also on bus traffic. If we increase the line size, what happens to each of these four classes of misses? I'd like you to answer that question. And if we increase the line size, what happens to bus traffic? Well, of course, it increases because for each miss, more data needs to be brought in. So it's not clear which line size will work best. Let's look at the first three benchmarks. In the case of LU, we see that the larger block sizes perform much better. In the case of radiosity, they do up to a point. And in the case of Barnes, well, as you increase block size past 64, you get an increasing miss rate. So results from those first three applications seem to show that which line size is best. Well, it looks to me like it'd be somewhere between 64 and 256 because Barnes doesn't increase in miss rate as much as LU decreases, and radiosity doesn't really matter much over that range. For the second set of applications, though, we see something different because they don't fit in the cache. Radix shows a greatly increasing number of false sharing misses with increasing block size. You can see that right there. But then when you look at bus traffic, you see that large line sizes generate a lot more bus traffic. And that's true pretty much for all of the benchmarks that we studied. So addressed bus traffic, however, moves in the opposite direction from data bus traffic. And you see that if you look at these white boxes there, because that's addressed bus traffic, mostly much less significant than data bus traffic. But the reason that that moves in the opposite direction is with larger blocks, you need to send the address of fewer blocks across the bus. So to the extent that it matters, well, address bus traffic does decrease, but the effect is swamped by the change in data bus traffic. And so with this in mind, it appears that a much smaller line size is actually best. We don't want to run up bus traffic needlessly. So 32 or 64. And they're pretty much among the most common bus sizes in use today. Excuse me, I mean the most common line sizes in use today. Now let's look at context switch misses. As cache line size gets larger, there are fewer uniprocessor cache misses. But that's not really true when you consider the situation where multiple applications are running at the same time. The number of context switches may go up as it does in some benchmarks or down as it does in other benchmarks. By the way, these simulations were done by Dr. Solahin for the 2016 text, so they're much more recent. Why misses go up? Well, because in a larger cache, there are more lines for a context switch to displace. So that means there's more lines to recover once you switch back to the original process. At the same time, the number of context switch misses could go down. Why is that? The cache could become large enough to hold the working set of both tasks, and then few blocks need to be replaced. Reordered misses also decline as the cache becomes large. Remember, reordered are because cache lines were shoved down to the bottom of the LRU stack and got replaced. And so, if the cache is larger, there will be enough lines in the cache that blocks farther down the LRU stack don't get replaced. They can stay in the cache. And so you can look at some of the numbers here and see that in some cases, number of context switch misses goes up with larger line size, and sometimes it goes down. I'm sorry, with larger cache size. Sometimes it goes down.